Hello everyone, very good evening and once again welcome back to the session. So today is our last day for our domain analytics, which is media analytics, and we are going to discuss about neural networks, which is a deep learning algorithm. So okay, so this is a deep learning algorithm. So deep learning algorithms are very rich in algorithms where we have neural networks, which is one of the very famous algorithm, where it has many hyperparameter tuning factors, which will help you to get a very good accuracy of the any model you build, and you need not do any feature extraction here. It automatically does feature extraction, right? But this is called as a black box technique. It is called as a black box technique. This is advanced algorithm, and the math behind it cannot be explained. The math cannot be explained. So just like we have seen for gain and we have seen for decision tree, now we are seeing for this. We know what is the equation, Euclidean distance. Here you are having the information gain expression, and here you are having neural networks, which is not exposed or which is not understood. So the advantage is that you are using this not only for regression, you can also use it for classification models. Okay, it is used for regression and it is used for classification. The main idea behind this neural networks is that they have taken the neuron cell and that neuron architecture they have dumped into this. So it is nothing but they are doing a mimic of a human brain. So when we are dealing with this mimic of human brain, it's nothing but you have, sorry. You are having neurons in our brain and they are taken the functionality of neuron. Here they have taken the functionality of neuron here and they have depicted it as an architecture and they call it as neural network. It's a brain functionality, what it is doing artificially, which it became a ANN algorithm. It's basically not an algorithm. We have to design our own network, own architecture here. So which is giving you very good understanding of what are the input features, etc. So the point here is when we want to work with this, how a neuron works. If you observe now, when we are watching a YouTube channel, suddenly we could hear some the music is being played. You're watching a YouTube video and you have the volume. Suddenly the volume was increasing in the video itself. The voice signal like this, the speech, whatever you have seen is like this. Suddenly it would increase. Suddenly what you will do? You will shut the volume down or you take out your earphones from your ears and you stop listening to it, or you reduce your sorry, you reduce the volume. So what is happening here? The same thing here also. You are trying to fetch that particular instance, and here we are trying to use that architecture. all the information here, it is being captured by the dendrites. So from the ears, from the hands, from our eyes, all the information is being captured from the dendrites, which is nothing but your input. Which is nothing but your input. But what is the other way around here is you have a tube, which is the output, where this is called as action taking scenario. When the information, like you're listening to the music, yeah, you're listening, volume is slightly getting up, increased. So you're still listening because your resistance is happening and there is no signal coming back from the axon to your ears that you should take some action. And this got filled up in such a way that now you cannot tolerate the volume of that particular song, whatever you are listening, right? It by default it has got increased. What will you do? You will pull out your earphones. That is the action taking scenario. So this is nothing but you call it as a cell body, and cell body accumulates the information here. Cell body, when it is accumulating the information, this information is taken and it is used for further analysis. Okay, it is used for the further analysis, the action taking scenario. So here, what are your inputs? The inputs are nothing but your dendrites. What is the output? Here you have the axon. Intermediate, you have the cell body. Using this architecture now, using this, they have built an architecture that you have your inputs, your X1, your X2, your X3. Now these are connected here to the cell body. They are connected to the cell body like this. So you divide this into two parts. Okay, here the data is getting accumulated. This part will take action and this is your output. This being your axon, this being your dendrite, this being your cell body. This is one unit of your neuron and it is called as perceptron algorithm. It is called as perceptron algorithm. We are doing a mimic of a human brain. So when the action taking is happening, when the action is going to take place, the same concept here, brain with a neuron, is used, which is nothing but when you take multiple units, multiple inputs, right? Don't look at this line, but multiple units into the cell body, and you're getting the output. The interconnection with neurons, what is happening in the brain, the same interconnections will happen here also. Like this, it is very, very clumsy, and it's just like that. You have billions of neurons in our brain, which are helping us to do any task very, very easily. Like it is a multitasking process which is happening very, very appropriately without any lag. Right? So now the point here is how we are using and how this is going to work. Basically, when we talk about a scenario of deep learning algorithms here, there are, suppose now you have the architecture designed like this, okay, and you are making it into output. This is your input, cell body. This is what this is called as perceptron. Okay, it is called as perceptron algorithm. Only one unit, whatever we have seen. Okay, but what happens here is when we want to work with this, okay, right, we are having two things to be added up here. Sorry. We have two things to be added up. These are nothing but you have one part is that you have integration function and you have activation functions. These activation functions, they take action. These integration function, they combine all the signals and they do. So how it is going to look? Okay, so what is happening here? The point you should understand here is when you are, how is that particular picture going to be? If you have these inputs, okay, you have these inputs, and these inputs, they are getting connected to a cell body, and this is the output. Now we have the data which you will take upon like this. This is the data. Now this data is passed to this particular people. Every data point, you have 1,000 data points here. So the first one you do is you are having the same regression equation here. That is nothing but okay. So what we are trying to do here is when we get this equation here, the same replication of regression equation is done here. This is nothing but your bias, and if you replicate it, it is your beta naught. This is your x1, x2 input, x3, x4, x5, x6. There is nothing but w1, w2, w3, w4, w5. x1 w1 plus x2 w2 plus x3 w3 plus x4 w4 plus bias is nothing but your y hat value. All these get merged up here, they got integrated here, which is giving an activation function. This is your y hat. Already y is there something here. This y and your y hat is going to y and your y hat, they are going to give you the difference. So here you have something called as loss function. Here you have something called as loss function. What is this loss function? Loss function is nothing but for each and every data point, if you are trying to find out the difference, that is called as loss function. E1, E2 till E1000 you are getting loss functions. How many? 1,000 loss functions you are getting. You are getting 1,000 loss functions. So this is going to, these loss functions, if you aggregate them, like you take the average of them, this is nothing but your cost function. This is nothing but your cost function. This cost function means average of all the loss functions. Till now we were only telling that this is a loss function, this is a cost function, the error function. Every time it's the same story we are telling, but now from now it is not the same story. It is quite different. We say that if you are having a linear separable data and your model is working absolutely fine with this, right, and you are having this algorithm would give 100% perfect classification happens here, and this line is nothing but your equation of a straight line b plus mx. The setup is called as perceptron algorithm. So this is loss, and you are doing this. Now what is going to happen here when you get this loss function? When you're getting this loss function, now what is the output you're getting? B, Wx, Wy. If this value happens to be 0.8, and what will you do? The value, whatever value you are getting, if that value is greater than 0.8, means greater than 0 or equal to 0, put it as 1 class. If it is less than 0, put it into 0 class. It is nothing but like, not like. Right? A person, by looking at the ad, a person liked it and a person did not like it. Okay, a person liked it, a person did not like it. 1 or 0 scenario. So that is your y. That is your y here. Now, based on these loss functions, whatever you got with this your cost function, you are going back and you are updating the weights. You're going back and you are updating the weights. These weights are initially given just like that. Okay, these weights are just given like that initially. Okay, they are given just like that by the algorithm initially. We don't know how these weights are given. So suppose we are taking a consideration here. When you are going and you are updating your weights, these weights should be given in such a way that you get the least error. The weights are adjusted like that. But now where the weights are starting, we are clueless. We don't know where the weights are starting. It's just like this. 1, 2, 3, and 4. Okay, this is 1 and this is here. The weight may start here, the weight may start here, the weight may start anywhere. And these are your weights. For every weight, you have like this. If the weights are starting here, they may decrease, they may increase. We don't know. The main aim is here to minimize the error. So the main aim to minimize the weight, going based on this cost function, you are going back and you are updating the weights. It is called as back propagation algorithm. It's called as back propagation algorithm. Okay, it's called as back propagation algorithm. It's going back and updating the weights. Again, it will calculate the error. It did not, if the error is not come down up to the mark, again it will go back. It will update the weights. It keeps on doing this for a bunch of times, which is nothing but you call it as epochs. You call it as epochs. Number of times the weights are getting updated is there in your hand. It is your choice. How many times you update the weights? Right? So all the observations they are passed through the network one time, we call it as one epoch. All the observations they are passed through this network one time. Okay, this is called as one epoch. It's called as one epoch. The batch gradient descent optimizer. There are different ways to obtain the weights. So batch gradient optimizer. Optimizer means just now we have spoken about the gradient optimizer, which is nothing but we don't know, just like a blind person climbing up the top of that mountain, closing his eyes and he tried to throw a ball. So the ball can come down at any steps, number of steps. If he stood here and he threw the ball, it will come down quickly. If he will stand here and he'll come down, it will come down quickly. Where did he stand? He himself don't know. But our aim is to reach to the convergence point. To reach to the convergence point very, very quickly means it is taking very, very less computation time here to solve this. Okay, within one epoch, if within one epoch it passes all the observation once and it will calculate the cost function. It will go back, it will update the weights. This is a generic thing what we do. This is called as batch gradient descent optimizer. Every time you update the weights, Every time you update the weights, it is called as iteration. It is called as iteration. So stochastic gradient descent, minimal gradient descent, Adam optimizers, gradient gradient descent. These are a bunch of things what you can use as an optimizer here. So the way you want to give training and the way you want to train your model and the way you want to change the weights, how many times you want to update the weights is all that scenario which is going to change. The point here is this MLP, it is, this artificial neural network, it is going to work. Your perceptron algorithm is absolutely fine for linear separable data. It is absolutely fine for linear separable data. But what if you have your data in a non-linear pattern? If your data is a non-linear pattern like this, generally you want 4 different lines. Here the data is like this, a spherical kind of, right? So what this perceptron algorithm, this is setup, if you pass such data here to this to classify it to this, right? To classify this is not going to do the best classification. This is not doing the best classification because it is a non-linear pattern. It's a non-linear pattern. So what we have to do now, people thought that data scientists, the research people, they have thought we have to change this integration function. Instead of using an integration function, they thought you can use a quadratic function or you can use a polynomial function or a spherical function so that you can aggregate them and you can do it. But we are never sure that we have to classify data which where the spherical function would solve it or a quadratic function would solve it. The pattern could be anything, not always like this, right? You don't have a pattern always like this and like this. There are not only 2 patterns. Pattern could be anything. We should do like this, and you have to do separation like this. So people thought that we should not do this. We have to change activation functions. They could do this through activation functions and they thought they should add few other layers in the network. Okay, they have to add few other layers in the network like this. These layers they called as hidden layers. These are called as hidden layers. So how many hidden layers you want? Your wish. How you want to connect them, how many neurons should be there, how many hidden layers you want, all is the hyperparameters what you can do. All is the hyperparameters what you are able to do. Right? So this setup, what you are doing here is hidden layer concept and you call that setup as multi-layer perceptron. As multi-layer perceptron. So every setup would have integration function, activation function. Now, what are the different activation functions we have? This is a setup of your multi-layer perceptron. Number of hidden layers, our wish, number of this one. But how we are going to update the weights? There's a formula to update the weights. Okay, that setup what is there, see the output, check the error. If the error is more and you want to change the error, you want to decrease or increase the error, it is going to go and update the weights. How it is going and doing updating the weights? It is nothing but old weight less learning rate less beta into actual value minus predicted value into x1. right? It is nothing but old weight plus learning rate into actual value minus predicted value of the input. This is going to give me the new weight. For instance, if you see here in this slide, you have 4 data points and 2 class problem. It is a blue class or a red class. Now I just give this data to your okay. Okay. So now when you are getting this, it is nothing but you draw a line and this line is going to do the separation. This separation is nothing but, see here, actually 2 blue class should come this side and 1 orange class should come that side. But here you understood that blue and the one blue class is misclassified and it went and it sat in the red class. To a red class, no? Maybe this 0 class is 1 class. This is not up to the mark. So what will happen? If you observe the loss function here, the loss function happens to be high. So what will you do now? You go back here and you update the weights. How you are going to update the weight? Using this formula. Initially, you don't know where the weights are there. Those weights are taken, and if you see here, it is here. If you see the weights, these are the initial weights, what you got. Okay, these are the initial weights, what you got. But when you have to calculate the new weight, old weight plus learning rate is something what you give, that is also a tuning parameter what you have, and x and y. What are the x and y values? It is -1.5, right? So first if I am calculating for -1 into, actually it was a 0 class, you predicted as 1 class, which is nothing but you call it as 1/3. Okay, now this is for your x. The same way you calculate for your y also. What is this y now? 1 old weight, this is old weight. So 1 plus learning rate into actual value minus predicted value. What is was the actual value? 0. What is the predicted value? 1 into, which is going to give me a new weight. Okay, 1 plus 1/3. But into you should do your input value. Here it is a half. Here it is -1. No? This is my y. So I got here 5/6. Taking these weights, it got updated. It will go and see the straight line, which was a sleeping line, it changed to a slanting line, a kind of a slanting line. Okay, so this slanting line, right? This slanting line, which is not up to the mark. Again, you can see some error kind of thing here. So what you have to do again, you need to update the weights. So how many times you are updating the weights is nothing but the number of iterations you are getting there. You are doing it. How fast you want to update the weights? You want to update each time for each loss function, or you want to update for the cost function. That is also based on the optimizer you choose while you design your model. Okay, so when you do this, yeah, when you do this, here I got the weights now. I take these weights again. Old weight plus learning rate Okay, the old weight into, yeah, you are getting the old weight into new weight. Sorry, old weight plus learning rate into actual value is 0 minus 1 into x is minus 1. This is your new weight. Okay, again this is for x. Again for y you have here. This is my old weight, what I have here for previous slide, plus 1 by 3 into 0 minus 1 into half, which is my new weight for this. Calculate these two new weights, and this is nothing but your 2 by 3 into 2 by 3. So taking these data points again, moving forward, if you do the classification, this is this line. This is this line, which is nothing but it is segregating things. Perfect classifier is what you got, and correction of weights is done for n number of iterations. Right? N number of iterations. How many times you want to do? Sometimes what happens, if at all you are doing iterations, it keeps on changing. It got best classifier at your 5th epoch only. But what is going to happen if the 5th epoch is classified, you got it, and you see a constant, there is no change in that, you can stop. There is not much increase in your accuracy or the error or the loss function here. This is your perceptron algorithm. So this is something what you are going to change. This is nothing but this is your activation function. Different activation functions you can use. So if you change this, that is also one option. Instead of not going to multi-layer perceptron, you can go and you do this change. This is one option. Go for multi-layer perceptron or change your integration function. Okay. So these are the different activation functions which we need to use. What are these activation functions? Activation function is nothing but it decides whether at which point of time your neuron should be activated. So what is that you are doing? You are calculating the weights. You are calculating your weights, and these weights are giving you the output. But when it is giving the output based on the activation function, whether a neuron should be activated or not, right? What should be the bias to be added? The purpose of the activation function is to introduce some kind of non-linearity into the output of the neuron. How it is going to do? F is something which is coming as output for your integration function. Okay, F is the output of your integration function. If F is equal to 1 and you are using a step function as an activation function, okay, you're using step as the activation function. This activation function is equal to 1 if your F value is greater than or equal to 0. So if F is equal to 0, F is equal to 1, 2, 3, 4, 5, all these values, if they are increased also, the output will be like 1 or 0. So this can be used when you are going for a binary classification. Okay, you can do it for a binary classification. Suppose now when it is a ramp function, based on your F value, you would decide your this one. See how it is happening? If F is greater than 1, it's always a constant value, it is 1. And that value F is replicating whatever F, that is the output when your F value happens to be in between 0 to 1. If F happens to be less than 0, it is equal to 0. So these are your output values. So ramp function can be used. Then you have a sigmoid function where you want to do a binary classification, you can use this, which is the same signal function or link function output what you got, right? You are using ReLU. This is very for your CNN architecture, right? But the negative values cannot be mapped here properly. So for that, what we are doing, we have something called as leaky rail. This leaky rail is going to be some negative values also. If some negative values are there, see this ramp kind of thing, right? To overcome the issue of ReLU, you are using a leaky ReLU function, right? Leaky ReLU function. So whatever we are talking about, the number of hidden layers, the number of neurons in each and every hidden layer, all those are your choice. Which activation function? Okay, number of hidden layers, number of neurons in each hidden layer, which activation function, which integration function, number of epochs, number of iterations, which optimizer you want to use. All these is your choice. It is your choice. All these are given as a tuning parameters. Okay, now what is this error surface here? Error surface is nothing but now whatever we have understood regarding the weights. Here, this is the error surface here. This is the error surface here. And this error surface is giving you how fast you are coming to this convergent point. Right? See here, this is nothing but 3 iterations it took to reach to the convergence point. Like this. 3 are required for the convergence point. So what will you do now? You can give the best optimizer. You can give the best what you call it as number of epochs and a learning rate. So the choosing a learning rate is also very important, because if you give very high learning rate, it will jump like this. The weights have been assigned like this. So it might miss, there's a chance that it might miss the convergence point. Suppose you give very low learning rate, this will be like this. Means it will take 1 minute, 2 minutes to reach to this convergence point. To reach to the convergence point. Okay, so this is your gradient descent algorithm. So finally, let us do the hands-on and understand. So the design is our choice. Okay. For this, what we need to do is we need to install Keras. Okay. We need to install Keras. And if at all, you do TensorFlow. Okay. So basically, this is a data set. This is a use case where given a person's details, his ID, his year of birth, his education, his marital status, his income, right? When we are given this details, so what we are going to do is we will do the classification. So what is that here? If your number of kids home here, kids home is nothing but number of small children in the home. Teen home is nothing but number of people who are teenagers in the customer's household. Okay, purchase date. Okay, it is called as purchase date. So like this number of days since the last purchase is recency. Right? This is nothing but the amount spent on wine products in the last 2 years. Right? Number of visits per month. Right? And you have here accepted CMP3, but if the customer accepted the offer in the third campaign, He has accepted the offer in the 4th campaign. He has accepted in 5th, 1, 2. Right? So these are here campaigns. Now, what is the other thing here? You have any complaints raised? Okay. You have any complaints raised? Like a bunch of things are taken and you are predicting the response. Okay. You are predicting the response. So first you are taking so what is you are doing? You have your NA values here. All are NA values, it will give you true or false. Now it is, if you observe here, you have income column, that 24 NA values. Data types also, it is a combination of integer and object type. So these are the bunch of columns what we have, and we need to predict the response. Means did he purchase or did he purchase? If you have purchased, when he has purchased, the first campaign or second campaign or the third campaign, he has purchased it. Okay. Now here, now the income column is anyway not, we have missing values, right? Instead of dropping that, we will go and import simple imputer. Okay, so simple imputer, missing values, we have done it, it is 0, and we have to observe the visualization. So good thing about neural network is that we need not worry about few of the things which are like skewness and all that. And we, if at all we want to do some kind of what we say is automatic extraction of the feature is done by default. Okay, you can also do outlier treatment for all the outliers, right? And we have checked that if you see the skewness, definitely you will have the outliers. Outliers are there only, we do that, right? Now comes this dividing your inputs and the outputs. Response, if you see, 0 is 1906, 1 is 34. So how you are going to build your model? Okay, first is that from sklearn.model_selection train test split x train x test y train y test train test split x comma y, test size is 20. This is my test size. So to build an your neural network data here, you need to check and you have to prepare your data. So when you do your data, first thing is that you should do the normalization. Okay, based on the data points, the kind of data you have, we should do normalization because all the data points should be in the same range. And if you see here, most of them are zeros and ones. Hardly here and there you need to do the categorical data to numeric data and vice versa. See here, few columns are there. So what we have to do, we have taken x and y separately. Now number of classes is equal to y test shape of 0. Right? Storing the number of classes into variable number of classes, it is nothing but taking y separately. It's a 2-class problem. Now comes the design section. You can design your own model. So first it is a sequential model. You will add 150 neurons. Okay, input you cannot touch, which is 23. You have 150, and you have the activation function here as ReLU. Okay, then you have 200 neurons, which is nothing but tan H. Again, you have 100 neurons. Again, you have 500 neurons, and you have the number of classes. How many classes? 1 or 0. Here, the choice is yours. You usually, when it is a binary classifier, you use a sigmoid. Right? You use a sigmoid. But now here it is softmax. So model.compile, you have to give your optimizer, you have to give your loss function, right? And you have to give the metrics, what it is. So generally you have If you have a lot of sparsity data, you can give sparse categorical cross entropy. Now you design it. You say that model equal to design MLP. So model dot fit is equal to, you're fitting your model with batch size is 950 and epochs is equal to 30. What do you understand by batch size? And what is this batch size? Batch size is nothing but you are dividing your entire data. Now 2000 data points, 1000 data points are there. You say batch size is equal to 10, 100. So 1000 by 100, which is equal to 10. Okay, it is called as 10. Now see here now. For 30 epochs, if you see gradually there is a loss function. You have the accuracy. See here, 30 epochs, it is 0.8521. If you evaluate it, model dot evaluate, X test, Y test, and verbose is equal to 1. Verbose is equal to 1 means it is going to give us the output in detailed manner. Okay, this is a loss, this is the accuracy. Right? If you print the accuracy, this is 84.59, it is the accuracy. Model not evaluate. Print the accuracy, which is nothing but train. So 85.212. This is our accuracy of the model. So what is that we are going to do? Which is nothing but here we are getting we are trying to use now different activation functions. We are having different loss functions. We are having different number of neurons. You can change your architecture. All these is our choice. Right? Here you are taking shape 2 class problem here. It is 23. It is sparse categorical cross entropy. Matrix is equal to accuracy. Okay. So thank you all so much for joining in. That's it. So this is our domain analytics for social media analytics. Thank you.